So now we're going to look at an example of bringing it all together, and one a little bit more complicated to look at a force and stress application. So here's our example. So we have 3 4-inch square support columns are being used to support a medium-sized deck. If the deck is 1,400 pounds of mass, how much stress is each support column experiencing? So there's quite a bit happening in this question, but our goal in the end is to say how much stress is each support column experiencing. So let's start with just sort of a diagram of what's happening and sort of visualize what's going on. So we have a deck that's supported by 3 support columns. So it doesn't really matter how you sketch it, but let's sort of think visually. Maybe it's a triangular deck and it's being supported by 3 support columns. So I'm going to put one on each of our corners. And that support column is a square. So we have 4 inches by 4 inches on each of our support columns. So we see that we're being supported here by a square, on top by a square, on top by a square. So it's just a sketch about what's sort of happening in that capacity. We know that the deck part of it weighs 1,400 pounds. So it is has a specific weight being pulled down by gravity. And then we know we have these support columns that have a force coming up. And we know that in general, since nothing's moving, that we have this sort of balance in our forces. But we would like to know how much stress is in each support column. So remember, that's force per unit of area. So we'll have to look at the area of each of those columns to say what is it actually supporting. So our goal is stress. So this is actually compressive stress, right? Because we're looking at that sort of push idea of happening there. So our goal in the end is going to be to find our compressive stress, which is going to look at the force over our area. And we only want that for each support column. So we have to sort of break it down and think about it that way. So we need both of those. Remember, force has to be in newtons, area has to be in meters squared. So we need to make sure we get those 2 values to plug into our formula. So let's start with force. So we've already sort of talked about that idea that we have this weight coming down. And we know that we have 3 supports coming up. And each of those is going to have a separate value. And let's call that our force compression. And we know that that's going to have to be broken down into 3. So let's start with our force. We know that these 2 are going to balance each other out, which means we can use our weight formula. So let's start with force, which ends up being the specific force is actually going to be equivalent to weight. So our weight formula is mass times gravity. So we already know that gravity is a constant, so we need our mass value, and we do have a mass. But important to note that it's actually in pounds, so we are going to have to do conversion before we plug into our weight formula. So let's do our conversion first. So our mass is 1,400 pounds, and we can go to our conversion chart and we can see what that conversion is to kilograms. So 1 kilogram is 2.205 pounds. So let's do a conversion to kilograms. So 2.205 pounds in every kilogram. So we know we're going to have to do a division here. So our mass is going to be equivalent to, when I put it into my calculator, 643.9206, etc. kilograms. And that's the value that we can actually utilize to plug into our weight formula. So weight is going to be mass times our acceleration, in this case is gravity, which we know is 9.81 meters per second squared. So when we plug that into our calculator, we end up getting a total weight or force of 6,228.5714, etc., newtons. So this weight is equivalent to our total compressive force on each of our support. So if we actually want to look at that idea that it's actually 3 of them that we're supporting. So our force compressive in 1 would actually take that whole value and divide it by 3. Right? So we know that we have 3 of them. So in one column, if we divide that by 3, we'll get the force in one of our columns. So force in one of our columns is going to be divided by 3, which ends up being 2,076.190476 newtons. And again, we want to maintain all of our decimal places, or as many as we can, until the very end. So we're partway there. We have our force in one column. So now we need our area component. So remember, we're looking at just one of our columns. So we have the force in one of our columns, so we can deal with just the area of one of our columns. And it does say it's a square, so 4 inch by 4 inch square. So let's do our area calculation now. So we have area. And we know the top, or the surface area, is going to be a square. So we end up looking at 4 inches by 4 inches all the way around. Area of a rectangle, we can look that up in our resource sheet, or just remember that area is equal to length times width. In this case, they're both the same. So 4 times 4 gives me 16 inches squared. But remember, we can't just throw that into our stress formula because it has to be in meters squared. So we do have to do a conversion from inches squared to meters squared. So again, we can go to our conversion factor chart. And here's our area one. So we have in 1 inch squared, there's 6.4516 centimeters squared. And then we can take it to meters. So I'm going to apply both of these two conversion factors. So 16 inches squared. And we know we can convert that to centimeters squared first. So that's going to be a multiply. So in 1 inch squared, there is going to be 6.4516 centimeters squared. So we do that multiplication, we're in centimeters squared, then we have to take it to the next step to meters squared. So we know that there's 10,000 centimeters squared in every 1 meter squared. So again, showing us a division by 10,000. So 16 times 6.4516 divided by 10,000. And I end up getting, for an area of one of the columns, surface area, 0.0103226 meters squared. So we have our surface area. We have our force in one column, so now we can just do the division of those two things. So we can plug into our formula, our stress formula, to find out what our value is going to be. So our force is 2,076.190476 newtons, divided by our surface area of one of our columns, which is given by that value. So 0.01032256, and I end up getting, from my calculation, 201,131.3546, and that's newtons per meter squared, or pascals. It doesn't specifically say in the question, but you usually want to take that to megapascals, so I'm going to divide that by 1,000,000, knowing that we have 1,000,000 megapascals pascals in every megapascal. So we end up getting approximately equal to 0.20 to 2 decimal places megapascals is our stress in each of our columns.